Page number 34.
Sir, 6 number.
Acha, number 6 is about the idea about stability. আচ্ছা স্টেবিলিটি নিয়ে তোমাদেরকে একটু পড়ানো হয় নাই মোস্ট লাইকলি স্টেবিলিটি বেসিক আইডিয়াটা আমি তোমাদেরকে বলি সেটা হচ্ছে I showed you some calculation for how the stability of an object can be operated. However, there are basic three factors that affect the stability of an object. Primarily there are two, but the third factor is also pretty important. The first factor is that the first factor that affects the stability of an object is base area. The second factor is height of COG. And the third factor, which is a bit optional, is weight of object, or you could also write mass of object. So the base area question is pretty simple. If we have multiple objects to compare which have maybe equal height and equal weight, might as well be made from different substances, but still the one that would have the wider base would always be the difficult to topple, or it usually always have the more stable orientation. For example, let's say if you consider multiple rectangular shape objects, let's say one is shaped like this, one shaped like this, and another one shaped like this maybe. So yeah, if you have these things standing on their bases like that, among this chain, if you want them to topple over, I mean, if you're going to push, apply a force on from the side, and you would expect them to roll to the side or roll onto the side and not slide, roll, that's important. So you do understand that this would be the easiest one to roll over because this is the thinnest base. So by applying the least amount of force over here, we can make this fall over because it has the smallest base area. So for the base area property, we say that this property affects the stability by more, less. More base area, more stable. Less base area, less stable. The second factor that affects over here is the height of COG. Height of COG means if we have objects which have approximately the same base area, among those objects, the one that has a taller height of COG would always be easy to topple over. For example, I'll go a bit elaborate on this discussion. Let's say if we have objects with equal base areas. Equal base areas means, let's say we have object of this shape and we're gonna draw objects of the same shape, but we're simply gonna draw objects which are of different height. Let's say one is of this height, and then let's say one is of this height. And if I draw another one of maybe that much height. So what I've tried that I have tried to draw objects which have approximately the same base area, but the center of the height of COG point is different. For example, here is the COG for this one approximately. Here is a COG for this one approximately. I'm eyeballing the diagonal crossing point over here, so about the midpoint, not essentially measuring them. Here is a COG over here. So as long as their base areas are exactly equal and they have different heights of COG, the one that has a taller COG or higher COG would be less stable. You do understand that because this object is actually pretty thin and pretty tall, it will be pretty easy to topple it over. So you can essentially roll them to the right, or you can tip them to the right side by applying the least amount of force that will be applicable for the third one. And this would require the biggest amount of force. Maybe all three of them will tip over, but the smallest effort would be required to achieve the rolling action, or the falling or topple over action is applicable for the one that has the highest COG. COG position is one of the very key factor for us to work in our regular life as well. For example, there is a question about shelves in this MCQ paper, which I would like to show you. It makes a very good example for this discussion. Have a look. This is a bookshelf where we have 4 shelves. So we want to stack them up with books, and we would essentially expect a shelf to be stacked in such a way so that it does not roll over, it doesn't topple over. We do not want an accident to happen. So we would always prefer to stack up the heaviest objects at the bottom of the shelf. Even in your houses, if you see that, if you have a shelf kind of stuff, you will always see that books or like uh, heavy, large showpieces, they are usually stacked at the bottom, and light stuffs or uh, small stuffs are usually placed at the upper shelves of the of a shelf. That's basically because we want it to be more stable. So among these four structures, which one is the question says number 17, this question says that books are placed in four bookcases as shown. Which bookcase is most likely to fall forward if pulled a little? So we are in this question, they are asking us that which bookcase is the least stable, or which one would require the least amount of force to topple it over if pulled a little bit in the front side. Well, obviously we're gonna look for the one that has the highest amount of mass distribution on the upper side and least amount of force on the lower side. So if you have a good look over
A.
here, this card response should be A because A has a big number of books on the upper side, so the COG height would be highest. B and C is somewhere in the middle. Among all of these four orientation, D should be the most stable structure. So this is also pretty important for us to understand that the height of COG actually affects the uh, stability of an object. This is also why, if I give you some practical examples for COG as well, in the chemistry lab, you'll see that we have different shapes of flux. For example, one of this example also shows up in this MCQ, which was, where is this MCQ? Not this one. Yeah, have a look over here. We have four different objects over here. Let me pick this up so that I can use it for discussion. Okay, so we have four different objects over here, and the question says some containers are made from thin glass. Which empty container is the most stable? So we have to judge that which is most difficult to topple over. Now you can see that B is standing onto a thin contact point because it is entirely circular. So it will be very easy to roll it over. You give a little bit of push or maybe blow air from the side, this is gonna roll over because overcoming this friction at this bottom would be very simple. C is pretty tall and pretty thin, which means the base area is actually quite small. A and D apparently have the equal amount of base length. You can see that this is quite wide. This is also quite wide. So in terms of base area, if we just take the first variable, in terms of base area, B and C wouldn't be more stable. A and D can be more stable. That goes for the first thing. And for the to compare between A and D, we can try and use the third so second variable, which is the center of gravity of the object. Center of gravity of the object means that we can actually uh, try to assume where the center of gravity of this thing is. Now I told you we were going through the discussion for center of gravity for regular objects that for triangular objects the height of center of gravity is usually 1/3 from the base. So if you try to guess that both the object, this conical flask and also this beaker, they both have pretty much the same height. So if I approximately guess their full height, let's say this is the full height of the object. This is the entire height of the object, and here we have the 1/3 of the height. Let's say this is the 1/3 of the height. So the COG of the conical flask might as well be somewhere over here. So exactly at the middle vertically, but 1/3 from the base. Whereas the COG height for the COG location for the beaker could be exactly at the middle for the two parts, maybe a slightly below. I'm drawing a slightly below the exact midpoint because the beaker is basically open on the top side, but it has a base at the bottom. So if you think about the mass distribution, if it was only a hollow cylinder, think about it. If you have a hollow cylinder, that has only the sides, like a basic cutoff from a long pipe, then you can pretty well be sure that the COG will be exactly at the middle. But then again, if you cover one side with a piece of mass, which basically makes you a beaker, so then there'll be more mass on the lower side compared to the top side about this point, which means your COG will be more closer to the side that is more heavier, because the idea of COG is that it is a center of gravity, center of mass, which means that it has nearly equal amount of mass on either side, either position, either side of the center of gravity locations. So this thing is going to be located slightly below the exact COG point. So that's why I did not prefer the top mark. I'm preferring the bottom mark. But even so, among all of these positions, I would say that the conical flask would be always the most stable structure. So A in this case is the character response. The reason conical flasks are so favorite for us in the laboratory is because they give our liquids very high amount of stability when liquid are kept inside the conical flask. First of all, because of the shape of the conical flask, they are stable because they are triangular. Their center of gravity are naturally pretty low, and they have a wide base, so they are not likely to topple over unless you are really having a wrestling with them. So conical flasks are not likely to topple over. So maybe dangerous liquids or more high acidic or high basic liquid, they can be safely kept inside the conical flask without higher risk of spilling them. Another beauty of conical flask is that actually before I go for the conical flask, let me show you for a basic beaker once again. Consider the shape of a beaker. Look from the side. So let's say this is a beaker. I'm gonna get rid of the top over here. আমার কথা কি বোঝা যাচ্ছে?
Yes, sir.
Yes, sir.
If you have any question anywhere, you can raise your hand or you can directly ask me the question. I appreciate that you're raising your hand. I'll definitely give you the floor. Consider the side view of a beaker like this. So let's say this is a beaker, and this is a beaker made up with regular glass, and it has uniform glass thickness all over. So let's say that's one structure. Let's say we have another glass that has pretty much the exact same thickness of glass for the walls, another beaker or maybe another glass, but the bottom is actually made from a much thicker glass. Let's say this beaker or this glassware has a thick glass base that is about this much thick. Let's assume. Now, between these two, when they are empty, which one is easy to topple over? Which one do you think would be easy to topple over, the left one or the right one?
Right one. Left one.
Which one would be easy to topple over? The left one? Left one. Because it has less mass at the bottom, which so this one will have a COG point. Well, then again, you should consider that if I try to assume, or if you try to visualize the diagonal cross point, and let's say this might as well be the diagonal cross point of the two corners, but the COG should not be over here because the top side is open, the bottom has some mass. So let's say that for this object, the COG is located over here. So let's say this is the COG point. So I'm just going to give a mark over here and erase the approximate diagonal. Well, we do understand if the COG of this beaker is located over here, the COG for this object will be even lower than that level. So let's say the COG of this object would be even lower, somewhere over here. So it would be located in such a point. I mean, what you need to understand or what you need to visualize that if this glass, consider this structure, this glass is essentially uniform on all sides. It's just a bisymmetric structure. For your viewpoint, because we are looking from the side, if you assume a vertical line, it would be symmetric on both sides. What it is asymmetric about any horizontal section. For example, if I draw a horizontal line and try to give you a bit of an idea what I'm trying to tell you, because it's easier to do in the computer environment. Let's do transparent selection, select up this line and have a look. If you try to divide up this glass piece into two equal parts with a section line of horizontal line, let's say if you cut the glass piece along this line and have these two pieces, you need to judge within your head that will these two pieces have equal mass or not. I mean, for example, if I place this line over here, you are definitely sure that top side has less mass and the bottom side has more mass, which means center of gravity is not located at this level. It has to move towards the more mass side. So if I slowly make this point line below, maybe because I assume this position of this point, maybe this is the position exactly through which if we cut the glass into horizontal section, we would get equal mass on the top and the bottom. And if this is a COG point, if this is a experimentally located COG point, this would be equally applicable for any other orientation as well. Horizontally, you can have that. You can also have that for a diagonal line as well. If you cut this glass in any orientation, even a perfect vertical line, doesn't matter. No matter how way you cut, the two opposite sides would always have equal amount of mass. That's the beauty of center of gravity. However, that was my point. So that's one thing. Another thing is that if we start to fill up liquid into this thing, for example, this was just a common example, so I'm going to get back to this example to give a bit of a better idea. Let's say we're now going to start pouring liquid into this thing. If as long as we're going to pour more liquid into this thing, the COG of this point is going to go down till the liquid level is up to this mark. Now, what does this information mean? Now, what does this information mean? Let's say I'm starting to pour in liquid over here. So let me just draw this with maybe a bit of an ash color to give a bit of a color differentiation. So okay. So let's say this is the amount. I have filled up the beaker with this amount of water. Now, what I want you to understand, if this is the amount of water that I have added to the beaker, now I have added more mass to the lower side. So logically, this COG point should get closer to the side where there is more mass. It's the same. It's a similar scenario to this one, but not same, because water is definitely less dense than the glass. So this one was much too denser. So a smaller volume would give a bigger mass. But here, water is of a less dense material. But anyway, we have added mass at the lower side. So this would cause the COG position to go slightly down. Let's say the new COG position. Let me draw those new positions with red. Maybe it's gonna come down a little bit. How much I do not know. How much lower is it gonna become? I cannot. I do not know that. But I can essentially say that it is going to be low, somewhat lower. So, and then if we add more water to the situation, let's say if I now label this with a red rectangle with a ash color field, just to give you a bit of a hint that how much is the new water level. Let's see if I add this much water over here, this dot of COG is gonna go even further down, and this will keep on happening. This will keep on happening till the COG point actually touches the water surface. Because if we keep on filling the water, you would have the lowest location of COG for this beaker. Lowest location of COG means that how low can you make the COG by adding a replaceable medium, for example, water into the glass. What is the lowest location of the COG of the beaker can be? That is possible. Let's say if this was the entire beaker, and this was the COG position for the empty beaker, and if we filled up this beaker with water by exactly this height, if we filled up water by exactly this height, this would mean that we have only added mass to the lower half, and the upper half is not allowed to have any mass, which means this part was added mass to, but this part was not added mass to. So in this case, if the COG gets down to, let's say, maybe over here, this is the most stable state of this glass that you can get by filling up water. Now, in place of water, if we just choose something heavier, for example, let's say if we choose some sand is heavier than water.
Mercury.
Or yeah, beautiful. If you choose some mercury, yeah, which is also a liquid, it is about 13.6 times heavier, denser compared to water. So if you choose mercury in place of water, and if you add mercury over here, we can actually bring down the center of gravity even further down. So the more heavier mass slash weight we're going to add to this object to the original halfway point, the more stable we can make it, and it will be difficult for us to topple over. However, if we keep filling this thing by water, let's say if we're gonna add up more water to this beaker and start raising this level, let me show you those additional level of water with maybe a pink rectangle with water inside. So this is the scenario. Now, whenever we are filling up the water above the original COG location, this is gonna start bringing up the COG position above and above and above. And ultimately, if we fill up the whole thing with water, let's say we have now filled up the entire container with water, this will bring the COG position exactly in the same position as it used to be for the empty beaker. So the empty beaker and the filled beaker would have their COG at the exact same position. But there's a difference. The empty beaker would obviously be less stable compared to a filled up beaker, because the filled up beaker has way more mass of itself, which means the amount of force you're going to require to topple it over to by applying to the from like this, and the amount of force that you're going to require to topple it over a filled up beaker on this direction like this is definitely going to be different. This would going to require far bigger force compared to this one. So this would be less stable, more stable between these two sections. এই discussion পরে না, এটা এখন compare করতেছে না. So if you're comparing between two big containers which are filled up, we're definitely going to have this scenario. This effect of having more stability by adding liquid to the structure is even more stronger if you consider a conical flask. For example, let's say I can actually draw a conical flask, maybe like that, and I'll take off the top. Oops, what happened? Okay, okay, beautiful. Actually, having a filled up conical flask doesn't help. Let's say this is a conical flask with the borders black.
You could take the triangle, cut off some part of his head, then add a rectangle.
Yeah, I'm essentially trying to do that, but ওই যে এটাকে ফিল দিয়ে কাজ করছিলাম তো ওই জিনিসটা ঝামেলা করতেছে. So let's say we cut this off, and I'm gonna hand draw the vertical parts because that would be faster. So let's say here is the conical flask opening. Disregard the bottom corners of this shaft. They are not supposed to be this shaft. They are supposed to be slightly rounded because of better usage and not chipping the glass and so on. The point is, because the conical flask has a shape like this effect of adding water, increasing the stability, is even more stronger or more powerful for a conical flask. Have a look. If we add, let's say the original center of gravity of the conical flask is over here. If we add some liquid on the conical flask, because you should understand, at the base, the cross-sectional area is very wide. As you slowly go up, the conical flask will slowly become thinner and thinner and thinner, which means if you look for the cross-sectional area, do you guys understand what is the cross-sectional area and the long sectional area? Did I tell you this ever? Do you know the difference?
sir.
Acha, let me show you. Let's say this is a solid cylinder, maybe which has a lot of stuffs within, we do not know, but from the surface it looks to be a solid cylinder. A cross section is a perpendicular section that is perpendicular of its axis. For example, if this is the axis of a cylinder, and if you cut off the cylinder along a plane like this, so let's say you cut along a plane like this, and you make a section like that. This is what we mean by cross section. So when the object is cut perpendicular to its axis, that's called cross section. And a long section would be if we cut along its axis. For example, if we cut this object, this is the cylindrical object. If we cut this object along a surface that looks like this, something like this, where it actually cuts the object through the halfway point. For example, it cuts the object along this side, so that you have one long side. For example, if a cake is easily cut to the middle, that's basically the long section. Or so that's the way it works. Now it's important for you to understand long section and cross section. For example, if you think for a human being, if they're cut from for example, if for myself, if I'm cut from my head through my bones all the way to my feet vertically, that would be my long section. No matter how you cut, whether it cuts through my face or it cuts through my ear, if it is cutting from top to bottom, it is always be a long section. But cross sections can be cut in any place. If my head is cross section, we're gonna see brains and stuff. If my throat is cut, we're gonna see the veins, artery, and the vocal cords and other stuffs. So having cross section can give you the individual cross sectional view for different parts. So that's the cross section and the long section difference. It's important that you understand that difference, because whenever you'll be writing these parts, it will be easier for you to express your ideas in cases. So if you think about the cross section for this conical flask, if means if we do try to consider the circle of different layer starting from the ground, closest to the ground or closest to the ground, you'd always have the wider circle. So the conical flask is very wide at the bottom or at the base. As you slowly go up, the radius slowly become smaller and smaller and smaller and smaller. Why this observation is important? Because it tells us that if we start to pour equal amount of liquid or equal volume of liquid into the conical flask, the more closer to the bottom the liquid falls, the less height it is going to gain. For example, let's say if this conical flask has some amount of volume, I don't know how much, but let's say if we start to fill up this conical flask with 100 milliliter of liquid, let's say the first 100 milliliter of liquid makes your height rise up to this much. Let's say the first 100 milliliter of liquid makes your height rise by this much. So you now have the water filling up this void space. If you add another 100 milliliter of liquid, you're going to have a bit higher volume rise. The reason being is that here we have a much bigger cross-sectional area, so the liquid could actually spread out more. So they gave less height rise. If we add another 100 milliliter, it's going to have even bigger height rise. So the further you go up, the same volume of liquid is going to give you even bigger height rise. And it is only going to happen as you go further closer to the structure. So if you're working with a small amount of liquid and if you actually put it onto a conical flask, it is basically not going to give you a significant height rise of the liquid, because the liquid is going to be pretty much spread out at the bottom or at the base of the conical flask, which gives you a much bigger advantage, because this presence of liquid, for example, let's say all of this liquid is not present. I'm going to color up the lower part. Let's say this is the liquid which is present right now. Let's say this is the liquid that is why. Okay, let's say this is the liquid that is present right now. So this will essentially lower our center of gravity. For example, let's say initially if the center of gravity was located exactly at this point, by adding a liquid of this much, center of gravity would become even lower. If you add liquid even up to this level, your center of gravity will become even lower. So as long as you do not fill up the conical flask, which is pretty unlikely for conical flasks, we do not usually fill up conical flasks. We typically fill up the conical flask to a point where it is easier for us to use, and the liquid will not topple over about halfway or maybe 1/3. That is a typical measurement you'll see in conical flasks. The whole idea of using conical flask is to give the liquid a more stability, so that the liquid itself and the shape of the conical flask together, they add more stability to that container, so that it is less likely to topple over. বুঝা গেছে কি স্প্রেডিং আউটের আইডিয়াটা and this increasing height of the liquid, এটা কি বুঝা গেছে সবার?
Yes, sir.
Any questions so far? Anyone? Acha. This was the part for the height of COG, and the third variable is weight of object. This is actually pretty simple. Weight of object is a very basic thing. If we try to consider the effect of this idea, where these two things are considered similar. For example, if we have two objects placed side by side who have the same base area and same height of COG, which means they basically have the same shape. Let's say we have two rectangular pieces of object, but they have different weight. If you wonder how, well, obviously they have different densities. So let's say this is made from wood, this is made from iron. So they have they obviously have different weight, because they have different density. obviously you do understand that this would be more stable compared to this one. This would be easier to topple over compared to this one, to topple over this one, because this is more dense, this is more mass, this is more heavy. Although you can see that I have tried to make the other two variables incomparable. Incomparable means that I have made the two base areas exactly equal for each other. I have at least attempted that, and I have drawn equal size rectangle, which means their height of COG is also at the same level. But even so, the one that is heavier would always be more stable. So that's the effect of the weight. It's not a very visual point. It's about more about the information that what are the material of this object. So which one is going to be more stable. So you have to remember that property if it comes to play in appropriate cases. If the question ever asks you that write the uh, uh, variables that affect the stability of an object, prefer to write. If it's a 1 mark question, you can write any of these. If it's a 2 mark question, prefer to write these two. And only if it's a 3 mark question, write this one. That's why I wrote optional over here. This is a point that is least highlighted in your syllabus. These are the 2 points which are most highlighted for your syllabus. So try to stick to these 2 questions for a 2 mark answer. It's pretty unlikely that right conditions of stability is going to have 3 marks in it. But if it does, in the most even in the most unlikely scenario, go for the third point. If it doesn't have 3 marks, preferably don't write that. But you have to remember this as an important factor because this actually plays a pretty interesting role. So going for question number 6 over here, from which I actually jumped to the discussion for the stability. Which one now do you think would be the least stable? Have a look at the shapes and try to give it a go. Number 6, if filled up with liquid, which one would be least stable? Hello? Pulaban, consider some basic stuff. First, consider the base areas, and then consider the center of gravity, height of the center of gravity. Have a
B.
look at the base areas. Exactly, B is the correct response. But if you have a look at the base areas, this is really wide. This is also less wide than this one, but this is also quite wide. Compared to A and B, these two have wide bases, so they shouldn't be least stable. So these two should be less stable. Now compare their shape. If you start filling up this liquid, it's this one COG could be somewhere over here because it's an egg shaped, half egg shaped, somewhere over here. If you start filling up liquid, this will be getting more mass on the lower side of this thing. But this one has a small base and also pretty top, pretty high opening. So you start filling up this one, this would be very likely to topple over. I mean, with a little bit of force, you can really easily roll it over. So B is the correct response. বুঝতেছো? Well, one. In this case, which one would you think would be the most stable? B is the least stable. That's okay. Which one would become more stable if filled with liquid?
D.
D is supposed to be the most stable because you can see the biggest size, and also D has a really large amount of liquid holding capability, which means if you fill all of them with liquid, D is going to have the biggest mass of liquid hold within itself, which means it's going to become the heaviest comparatively from among all of them, which essentially can make it more stable nevertheless. Number 7, I think it makes sense. Which one is more stable? Obviously A, conical flask is always the most stable. I'd like to discuss for number 10. Number 10 is a pretty interesting question, which sometimes the students actually mess up. Have a look at question number 10. A flat lamina is freely suspended from point P. The weight of the lamina is 2.0 Newton and the center of mass is at C. The lamina is displaced to the position shown. What is the moment that will cause the lamina to swing? So what is the moment that is causing the lamina to swing? So let's paste this picture over here and let's have a detailed look over here. This is the current orientation of the lamina. Somehow this lamina is held in this position, somehow maybe by holding by a hand or by some other support mechanism. But this lamina is trying to get stable. This is not a stable condition for the lamina because the support point is not above the COG point. This is the COG point according to the question. This is the center of gravity, is the COG over here, and P is the pivot where there is a pin labeled, which means we are trying to hang this lamina hanging from the P point where C is the center of gravity. The question is asking us that what is the moment that is working on this lamina at this orientation, trying to make it stable. This is actually pretty simple question, but the reason students actually mess up quite a lot sometimes because there are three different dimensions given. Just to test your understanding for the moment question, you have to choose carefully which of these discussion are you going to use. I'm going to give you some heads up. Try to have a look. The weight is going to work vertically downwards. Any object's weight always works vertically downwards no matter what. So this is the working action for weight. This is your pivot point, and you want to find out the moment. You want to calculate force into perpendicular distance. So এই পয়েন্ট থেকে এই লাইনের উপর যে পারপেন্ডিকুলার ডিসটেন্স হবে সেই পারপেন্ডিকুলার ডিসটেন্সের লেন্থ কতটুকু হবে? Did you guys get my question? Hello.
No.
Sir, is it going to be 0.30 meters?
Yeah, that is the correct response. What I'm trying to tell you is that this is the part of the question that you should be able to process pretty easily. I have drawn the weight over here, whatever the weight that is actually, no, not whatever, they have given us the weight. This is equal to 2 Newton, might as well write that. So this 2 Newton force is working vertically downwards from the center of gravity C. P is a pivot point. To calculate the moment, we need to draw a perpendicular line from this pivot point onto this force line. Now, I've told you earlier that whenever we are trying to do that and the force line is not in a convenient position, for example, if the force line was placed over here, we could very easily draw a perpendicular line, because no matter how many lines do we draw along these orientations, like from here to this line, or from here to this line, or from here to this line, no matter how many lines do we draw here, we cannot get a perpendicular line. So essentially, to draw a perpendicular line, what we have to do, we have to extend this weight line. Why does it change every single time? Okay, we have to extend this line slightly backwards, which we can do, and then we can draw the perpendicular line. So if you now draw the perpendicular line, this will be a perpendicular distance, which will be perpendicular onto the force working line. And QC is, if you now have a pretty good at this thing, you basically end up with a rectangle. Do you see that rectangle? Basically end up with a rectangle. This is your perpendicular distance. The question is, among these three distances, PQ, PC, and QC, which one actually represents the D? D is represented by which one? This would be QC, right? So QC is the correct perpendicular distance that you have chosen, and then the rest of the part is pretty simple. You just multiply 2 into 0.3, which gives you 0.6. There is only one option for 0.6, so that basically makes your choice much too simpler. It's a clockwise moment, because obviously if you are hanging from this point, this is the working force, the object is going to try to rotate to the left, which makes it a clockwise rotation. আচ্ছা, বুঝা গেছে কি ডিসকাশনটা সবার? দেখো, is it clear? If you have confusion, you ask me. Take a good look at the figure. If you have anything to ask, please respond. I'll help.
Sir, why QC? Could you repeat that part?
কোনটা আগে বলো?
কেন হচ্ছে?
মানে এই মোমেন্টটা কেন এক্সিস্ট করতেছে?
I was confused between that the part where you wrote distance and QC. So why not the part where you wrote D and circled it, but not QC?
Oh, because I was trying to draw a perpendicular. Yeah, I get your question. I was trying to find out the perpendicular distance from the pivot point to the weight line. So D is basically my perpendicular distance, which by geometry is equal to QC. Or if you want to, because usually the perpendicular distance is drawn from the pivot to the force line. That's how it's convenient to draw. But Q in this case is not the actual pivot point. P is the pivot point. So this is the perpendicular distance that I want to do my math with. And from this rectangular orientation, QC is basically equal to D. That's why I marked D as the perpendicular distance. QC can be also said to be the perpendicular distance, because this QC is also essentially perpendicular onto the force line. But because Q is not the pivot line, that's why I did not label this. But if I did circle this one, might as well, this wouldn't be a wrong thing to do, because that pretty much means the same thing. Did it make sense?
Yes, sir, got it.
Beautiful. So এটা গেল this was a pretty interesting question. এটা কিন্তু খুব frequently তোমাদের পরীক্ষায় আসে. For what I've seen that in school exams, this is a pretty common question, and smart teachers do interesting things. They swap out these option choices. So you have to be careful that which one is the actual value, or sometimes they can actually edit up these numbers. Editing these numbers is actually pretty simple. I mean, anyone can edit these numbers and have a different expect a different answer over here. So read the question carefully, see if your school teacher have edited these numbers or not, and do your own calculation, and then try to get the correct answer. Don't just memorize this question and try to give a correct answers. This would not be a good idea. Number 11, have a look at number 11. Number 11 is a pretty interesting question. It takes a good amount of observation capability. So have a look at number 11. Might as well zoom out a little bit. Zoom out করলে তো আর দেখা যায় না. So let me get rid of this bar maybe. It's a bit more visible now. That's the best view I can give you. This arrow is finished over here, right over here. Or maybe I can make it a bit more longer. Yeah. So এখানে দেখো, which one do বলো রাখো পরে, which one do you think is the correct response?
Sir, B.
B.
Now, there is a interesting information that you need to consider. Have a look. Before I tell you the answer, well, you might as well know the answer from the answer booklet, but I'll give you my discussion. Two blocks are placed on a beam which balances on a pivot at its center. The weight of the beam is negligible. Which beam shows the forces acting on the beam? For your convenience, I mean, which goes on your convenience side, is that the size of these two beams are exactly, size of the two blocks are exactly equal. So, and the question says the beam is perfectly balanced, and it says also inside the bracket, the length of each arrow represents the size of a force. Now, remember, if we have to have equilibrium on an object, we need to fulfill two requirements. We need to have equilibrium of forces. We also need to have equilibrium of moment. We need to have fulfill two equilibriums. Now, which one shows you, I mean, these two does not show you equilibrium of forces, because the right force is a lot longer and the left force is smaller. So none of us should give A or C by any logical reason. We can be confused in B and D. Now have a look. B and D, they both have equal amount of force on the bottom side. Whereas to fulfill the equilibrium of forces, we must have equal amount of force on the top side as the downside. Now on the lower side and downward direction, we have two forces. So if you sum up the arrow lengths over here, you're going to get a much longer arrow, and that arrow length should be equal for the top one. So you need to have a bigger force on the top side, which should be equally counterbalancing the downward two forces. So sum of the downward forces should be equal to the upward force. There's only one upward force available in this figure, which I can try to draw maybe from here. We're going to have one upward force from the pivot point, and we're going to have two downward force from this point. So the sum of these two downward forces must perfectly balance the one force over here. Now, in this case, okay, Asif actually asked me a question that what if we are considering the weight of the beam? Well, the pivot is placed exactly at the geometric center, so weight of the beam might also be a factor over here. If the weight of the beam was labeled in the question, then the sum of the three downward forces should be equal to the one upward force coming from the support of the pivot. So all the downward forces should be equal to all the upward forces. That's the basic idea. Since the length of each arrow in this case is representing the size of a force, so obviously the top arrow has to be significantly bigger compared to each of the lower arrows, which brings us to the correct response, B, not D. Because if you take a ruler and you have the question paper in your hands, if you take out a ruler and if you actually measure with your ruler, you'll see that each of these arrow sizes are exactly equal. This would mean that this upward force might as well be balancing half of the sum of these two. For example, if this is 5 Newton I'm just assuming numbers. This is also 5 Newton. This upward force is also 5 Newton, which means this whole setup is not in equilibrium of force. There is a resultant force downwards, which is not supposed to happen. But if you assume this one, this is 5 Newton, this is 5 Newton, this arrow has nearly exactly the double length of this arrow. So this would be 10 Newton. So which means that this is an equilibrium scenario. বুঝে গেছে? Everyone? এরকম আরেকটা কোশ্চেন হয়, আমি সিমিলার আরেকটা অপশন দেখাই। ওই কোশ্চেনটা অ্যাকচুয়ালি খুব সিম্পল, but might as well actually change this figure a little bit. I'll have to copy up this figure and edit this a little bit. Let's say this level, this level. আচ্ছা, আমি এইটুকুই একটু কপি করে নেই। কি করলাম? Control C. In some other cases, sometimes they give you a figure, or they say that the situation is perfectly balanced, but simply to mess with your minds, they do another thing. And that thing is, sometimes they make one of these bar taller, like that. Maybe taller, all the way taller, like this much. And give you the exact same question. 2 blocks are placed on the beam, which balances on a pivot at the center. Straightforward bole dise, it balances itself in the center. Which one is the correct response? Now, because this block apparently looks bigger, students tend to think that this is the correct response. Any of the A or C is the correct response. But don't be fooled. The question says 2 blocks are placed on a beam which balances on a pivot at its center. Which means even if this block is slightly bigger and this block is slightly smaller, they are perfectly balancing it out. Now you might wonder, how is that even possible? Well, the blocks can be of different dimension. If they are made from different material, you might as well think this is made from a denser material, maybe iron. This is made from a lighter material, maybe wood or plastic. But if they produce equal balancing on the 2 sides of equal length from the pivot point, their weight would be exactly same, but their dimension can be different. So sometimes this question also shows up, and for this question also, the correct response is also B, because the sum of the downward forces should be equal to the upward forces. Just because one of the block apparently looks to be taller, don't feel confused that this will have a bigger weight, because there is no mention that they are made from the same material. Bigger block means it has a bigger volume, but the weight that they produce are exactly equal to each other. Did you get my point? বলবান বুঝছো কি বলছি?
Yes, sir.
Yes, sir.
It's a word of the question. It's a description of the question that's pretty important for you to understand. Just because a bigger block is there, don't presume that this bigger block should have bigger weight. So the pivot part should be located on the right side. If the question anywhere say that both of these blocks are made from the same material, which means they have the same density, then obviously this one will have a bigger weight. In that case, to have the balancing, the pivot has to be placed somewhere on the right, so that we have less length over here and more length over here, which basically is the principle of moment. But for an identical question, a different figure, still the correct response would be D. Sorry, B, where we have bigger force on the upward side. Okay, anything else from this page? Anyone? Dekho. Anything else you couldn't do from number 35, page number 35? Acha, Asif, you can write this in public chat, no big deal. Don't write me privately, so that if people don't actually get your question, because your first question was actually pretty interesting. It would be helpful for everyone if you really write them. If you're writing me anything in the chat, if it's not exclusively for me, subject related questions, preferably write them to everyone, so that everyone can see that. I'll discuss 23, no big deal. Let me finish this page. Could you please do number 13 properly? 13 is actually an interesting question. I'll show you why I'm saying this question is being interesting. If you have a look at this question, the question is not asking you to find out the existing moment of the setup. Read the question. An uniform beam is balanced at its midpoint. An object is placed on the beam as shown. So the bar can be perfectly balanced. Now we have placed another object on the left side. Which force will rebalance the beam? Which means now we are trying to find out a force that should be placed over here so that the existing moment of this setup can be counteracted. So I can see it very well that the existing moment is anti-clockwise because the weight is placed on the left side. So if we allow the whole thing to move, this thing is going to go down. This whole plank is going to rotate about the pivot point to any anti-clockwise direction. So this is the existing moment of the setup is anti-clockwise. To make it rebalance, we need a clockwise weight. Now a clockwise weight must be placed on the right. If we are applying a downward force, it should be placed on the right. Or if we're placing an upward force, if you wonder how do we place an upward force, well, very simple. We can push it by our finger upwards. We can have a balloon, helium gas balloon, tied with a string anywhere on this plank, by giving us an upward force. So if we are trying to have a clockwise force, so let me copy this up so that I can make better sense to you. So we can have, what is happening? Okay, nothing very complicated. So if we are, so the existing moment for this question is anti-clockwise. So to have it balancing, I need clockwise force. So clockwise force can be achieved by applying a downward force on the right or by applying an upward force on the left. So either of these two options can be correct. So by judging this basic reason, you can very easily find out which options cannot be acceptable. Then also, to rebalance it, the numerical value should be also equal. For example, in this case, the numerical value for the moment is 1800 Newton centimeter. I'm writing in Newton centimeter because all these values are also in centimeter. If you do the calculation over here, A gives you 1800, B gives you 1800, C does not give you 1800. Disregard the orientation. If you just do the mathematical calculation, 3 into 13 into 60, 1800, 13 into 60, 1800, D also gives you 1800, which means in terms of values, C is not going to be acceptable. Then you go for the judgment that which force is applied where. You need a downward force on the right or an upward force on the left. So we have an upward force on the left at the first question. This is an upward force to the right. Upward force to the right is not going to give us any rebalancing. Downward force to the left is not going to give us rebalancing. So A happens to be the only correct logical choice, which gives us a clockwise moment, which helps us to rebalance the beam. বললাম বুঝা গেছে কি? This is the reason I'm highlighting this question, because to be able to solve this question, you have to calculate all of these moments, and there is left and right, upward and downward. So it can be a bit confusing for your kids to do this thing, but just try to take one information at a time. To be able to solve this question properly, you have to do 5 calculation. Hypothetically speaking, you have to do the existing moment of this setup, and then you have to find out the individual moment of all the 4 option choices, and then you can only compare those values and eventually get to the correct response. Can take some time, which is all right, but understanding the question to its core is very important. Remaining questions are actually pretty simple. If we go down the line, this page, a similar question, have a look. A uniform beam is pivoted at its midpoint, and object is placed on the beam as shown for Newton per centimeter. Which force will rebalance the beam? I want you kids to attempt this question right now. For those of you who did not attempt the paper, try to do this. Solve this one. See if you can get to the correct response. I'll give you a minute or two.
A.
দেখছি দাঁড়াও। Yeah. In my observation, A should be the correct answer, but I want every one of you to understand and get to that answer. You can very easily discard C and D because the mathematical product simply isn't equal. They are 500, but you need 800. So C and D are out of question because the mathematical value doesn't make sense. Now between A and B, which one is logically more acceptable? বলবান, A is the correct response. সবাই কি আসছে?
Yes.
Anyone else? I had response from 2%. There are 13 more people in our channel. Please respond.
Yes, sir. I got
Yes,
it.
sir.
Yes, sir, I got it.
There are more people who are not responding, but I am assuming that you could do this. If you couldn't, please do respond. I'll help you solve it as well. But this is a very similar problem. That's why I'm not going into the details for this one. And then we have this question. Okay, 23 is a pretty interesting question. I'd like to discuss 23 in detail. 23 is a nice question, to be honest. Let's have a look at question number 23. A girl uses paper clips to balance a toy bird on her finger as shown. What is the effect of the paper clips? So this toy bird is sitting onto the person's hand, which means this hand is working as a support point, which means this toy bird can rotate about where it's sitting. So it can rotate about my finger, left and right. If we are applying more paper clips over here, I'm making the lower part heavier, which means I'm bringing the COG further down, further down, further down. And applying enough number of paper clips, I can make sure that actually, let me copy this picture and maybe I'll be able to draw some stuff to make it a bit more clear. If there are few paper clips, or maybe if there are no paper clips, the tail wouldn't be as heavy as the upper part with respect to the finger. For example, if I try to draw a very thin line along the finger, for example, let's say if you try to think about the total mass of the toy bird, that is divided into half along this horizontal line. For the toy bird to be stable on the hand, its center of gravity should be below the point, below the finger. So actually for the three-dimensional figure, it's a bit difficult for me to draw. So let me just try to draw this bird in a two-dimensional figure. For example, this is the head of the bird, beak of the bird, eye, a bit smiling, and then the body of the bird. Here is the finger. This is a cross section of the finger. So this is the leg of the bird, and here comes the tail. Okay. So let's say this is a two-dimensional version, and we have a bit of a wing as well. Why not? So the idea is that if the COG of this bird is above my finger, let's say if the COG is somewhere over here, or somewhere over here, somewhere over here, then it would be very easily for the bird to topple over, roll over, and eventually fall down. Because you're now basically trying to balance an object by supporting from the underneath. So if it starts to roll over, it's gonna keep rolling and it's gonna eventually fall down. So this is a situation that we call unstable equilibrium. It's in equilibrium, but it's pretty unstable. When once you start to roll over to one side, it is gonna keep rolling and it's gonna fall off from my finger. To have it balance, we would appreciate if the COG of this whole bird falls below my finger or below the support center. For example, if the COG is over here, in that case, what's going to happen? The weight of the bird is going to apply force downwards, and my finger is going to pull it upwards, and these two forces are going to pull apart in opposite direction, which can keep the bird stationary like that. Like I told you in the earlier case, is that if we are trying to make an object perfectly stable, we can hang an object from a single point support and the object be perfectly stable. hanging an object from one point is good enough for that object to be perfectly stable. But if you want to support an object from underneath, only 1 point is not good enough. 2 point is also not good enough. You need at least 3 points to have a stable support system if supported from underneath, for example, a table. So we would want the COG of this whole toy bird, to exist below our finger. Now, to achieve that, we have to increase the mass on the lower side. That's where these paper clips are coming in. So the more paper clips we are going to add to this tail, the heavier the lower half is going to be. And eventually, by after adding a certain number of paper clips, this COG of this toy bird is going to fall below our finger. It is at that point the toy bird will become stable on our finger. I mean, become stable means that even if we give it a little bit of a flick on left or right from any of the direction, the toy bird will oscillate a little bit, but eventually it will not roll over and fall from our finger. It will eventually stay on our finger. Even by a little bit of vibration, it's not going to be rolling off. So that's essentially what we are trying to achieve. So the question series: a girl uses paper clips to balance a toy bird on her finger as shown. What is the effect of the paper clips? So go through the option choices. They help to raise the center of mass above her finger. No, we are adding the paper clips at the bottom. They help to raise the center of mass to her finger. They help to raise the center of mass. So both of these questions are actually wrong, because we are adding the paper clips at on the tail side of the toy bird. So it is not essentially raising the center of mass. It is obviously lowering the center of mass. It is lowering the center of mass. The C number says they help to lower the center of mass below her finger, which I believe is a correct response. And then it says they do not affect the center of mass but increase the weight. Well, it does increase the weight, but that option is wrong. If you add mass to one side of the object, it will definitely affect the center of gravity. So altogether, the correct response is C only. বুঝে গেছে কিনা দেখো? Everyone. Okay, no response. So I believe there is no question. Asif Irfan, বুঝে গেছে? Was it clear enough?
Yes, sir.
24 is actually pretty dumb. Then the same question repeats itself. Acha, there was a mathematical question for that. There is a certain math question that I was planning to help you by. I drew the figure, but we did not solve the B part, that how far the person can move. Do you remember that question? From the notes, I think there was a question. I just remembered that. Let me check. I did not show you the solution for, where is that? Elasticity, moment. Center of gravity, COG lamina, stability balances. This one. I believe we did solve number A in two different ways.
Yes, sir.
And so A and B were actually done. Actually, I didn't solve number C. I'd like to show you the solution for C after we finish this MCQ paper. So let me just have this PDF over here. So anything from page number 38? I'd like to help you for number 29 can be a bit difficult for some people. A piece of uniform card is suspended freely from a horizontal beam, at which of the point shows its center of gravity. Now there is no mathematical or geometrical way that you can actually go for a perfect measurement for the center of gravity. But one thing you can know for sure, because it is hanging from the pin, the center of gravity is definitely below the pin. So A cannot be the answer, and D cannot be the answer either, because D is located on the edge of the thing. Center of gravity for non-uniform lamina is definitely inside the object. Between B and C, what you simply need to judge that if you just slice the object by two pieces along the line B, cut this object horizontally, would you have equal mass on the top and the bottom? Whereas if you cut the object along C, would you have equal mass on the top and the bottom? It's very difficult for you to measure because these are non-uniform shape. But which one it would give you more or less approximate in your head? I mean, which one is more likely to give you equal mass of pieces?
C.
C is supposed to be the more equal, will give you more equal on a mass of pieces, because if you cut along B, you can see that the top side is becoming a very small rectangular piece, or the lower half is a very large chunk. But if you cut across B, the top side is a rectangle and the bottom is becoming a trapezium. Maybe C can actually give you a more logical choice of having equal amount of mass on both sides. So which makes C our correct response. Question number 30 is actually pretty interesting. To solve question number 30, this is actually a test that is done for every double-decker bus before they are rolled onto the roads for safety reasons. So this is a pretty interesting question. So let's have a look at this question. The stability of a bus is tested. This is actually a double-decker bus. You can see that first deck, second deck. So the stability of a bus is tested by tilting it on a ramp. The diagram shows a bus that is just about to topple over, which means it is under the situation of critical equilibrium. Where is the center of the mass of the bus? Which one do you think is the center of the mass?
So I guess it's D.
Okay.
E.
C.
Okay. We have
D.
B, C, D.
E.
Anyone going for A? Maybe not. Okay, I'll help you to solve it. Before I tell you the exact correct answer, let me help you to solve it. Try to understand. The bus is having its stability with a base area that is basically its two wheels, which means if you consider the length from the very left of this wheel all the way to the very right of the wheel, this is basically the total base area of this bus. You might wonder, why not only the wheels? Because, I mean, if you are having a table supported by 4 legs, its base area is the rectangle area covered by the legs, not the only legs. So it has 2 wheels. The base area is from the very left of the left wheel to the very right of the right wheel. So this is the base area. What we've seen in our earlier discussion, that the case of critical equilibrium is that when the weight passes directly through the corner of the base, which I should help you recall from this figure, this one. So this is stable. This is critical equilibrium, which means about to topple over, on the verge of toppling over. It's almost toppling over, any of those kind of words. And if this weight works perfectly out of this thing, then it is actually unstable. So if you remember this figure, we're going to apply the same idea to solve this question right over here, is that we're going to try to find out the center of gravity of this object by drawing a vertical line through from this point. Now, you need to use a protractor, or if you have a set square, it would be easier for you to draw this as well. Yeah, you can use your set square in this, choose your set square, and then hey, I'm not drawing. Okay, I want to select. Why do I have to? Okay, I can do freeform selection as well. No. You can place your set square in this orientation.
লাইনগুলো চলে গিয়েছে।
So you can place your set square in this orientation because you're trying to draw a line that should be vertical. So place one side of the set square base parallel with the ground, and place your set square so that your side essentially. What is this magic? So place your set square along with the bottom, and then one of the side should go through the corner of this wheel over here. And then if you don't have to draw essentially, but my point was to draw was that you could draw. You can see that this shows us that the weight is passing through one point of these 4 points. Which is that point?
C.
You do understand that because the question said that the bus is just about to topple over, means it's the case of critical equilibrium, which means it is marginally stable. So the weight has to go through the edge of the base of the whole bus. So C is the only logical choice, which means now if I just try to show you for the weight, if we do draw a vertical arrow from the C point, this weight is gonna work perfectly through the exact corner of the wheel. That's how this figure is drawn. And this basically means that this situation is about to topple over, which means if we just apply bit more angle, even a slight bit of angle, this weight is gonna fall out of the base and this bus is gonna roll to the left. This is an important test to check the stability of a bus so that we know that in a road, in a bumpy road, or whether this double-decker bus filled up with people, is it more likely gonna, is it gonna roll over onto other cars or pedestrians or not? That's a very important safety factor because this is a tall structure. So tall structures are more likely to fall over. But then again, to haul more people, we need double-decker buses in play in certain countries. So this is a very important safety test for double-deckers. Kids, do you understand why the COG is not over at B or preferably at C? I mean, why is it quite below? I mean, not exactly to the halfway point.
Yes, sir.
Why? Propose some reasons for that. I mean, this is from the figure. I explained the figure, but I'm asking that the actual I mean, structural reason of a double-decker bus, that why is it so that the double-decker bus's COG is so much below compared to the about half, if I draw the halfway mark of the height of the double-decker bus, maybe this is the vertically halfway mark. So why isn't the COG over here? Why is the COG so much below than this point? Why?
Sir, below there are people, so there's mass.
Well, this is an empty double-decker bus. We're not testing this double-decker bus with people
There
Sir,
inside.
are
because there
wheels
is
at the
more
lower
mass
part of the,
down, there's greater mass down the bus. So
Why?
that's why.
because the wheels are situated at the bottom.
So wheels are really heavy.
So there are motors, engines, and stuff like down there, right? So they give a lot of mass to the vehicle, which
Uh,
causes the
this,
center of gravity to go
this is
down.
actually both of your responses, wheels and also the motor engines. Everything together is actually connected to the lower side. And one thing I would like to, I mean, the reason I'm telling you this so that you have a better idea, that any car is made on a metal frame, which you call the chassis. Feels like this. It just spells like chassis, but the actual pronunciation is chassis. So this is called the chassis, which is the metal frame. So we have a metal frame, then ওই ফ্রেমের সাথে আমরা চাক্কা লাগাবো, ইঞ্জিন লাগাবো, আমরা হুইল লাগাবো, and আমরা ড্রাইভিং স্টিক লাগাবো, ওই ফ্রেমের উপরে আমরা পুরো গাড়ির বডিটা লাগাবো, and then the whole thing becomes a vehicle. So this entire chassis is always made from very strong, heavy materials. For typical buses like this, iron is the only preferable choice because it's cheap. For Formula One cars, they used to use aluminum, which is lighter than iron, but can give you the same amount of strength for a smaller weight. Now they have gone for carbon fiber, which can still give you a much higher amount of strength, but even lighter. So for performance cars, you need to choose lighter material with high strength. But for cheaper option, you always stick with iron. So you have a lot of iron structure. Let me draw the iron structure maybe with a bit of an ash color. You have a lot of iron structure located at the bottom of this car. And you have at least 6 wheels. So double deckers usually come with 6 wheels. You have 6 wheels at the bottom. And also you have a large piece of engine that is also made up of iron that is located on the lower side, not on the top side. So all of these masses make an uneven distribution vertically, which makes the COG significantly lower than what the geometric point proposes. And also, just to make sure that the COG of a double-decker bus is actually quite low. It's not really a high, because the lower it is, the more stable it is. We have just discussed that. To make sure that the COG of the double-decker bus is actually quite low, this deck, the floor of this this deck is usually made from very light materials. More common choice is wood. They use wooden planks to make this layer on which the seats and the people are stacked. If they don't use wood, they might as well use very high quality plastic, but they will almost never use a metal sheet over here, because using a metal sheet over here, even if they use a metal sheet, they're going to choose a very thin metal sheet, which is just good enough to support the people's weight, but not to add more heavy structure over here, because We don't want the COG to rise up. We want the COG to be as low as possible. So that's why this is pretty important. And this was a bit of an additional description, but give you some idea that how factors affect the design of a certain vehicle. This is also the reason that Formula One cars are so low. There is, I think, one paper 2 question that might show up in our paper 2 worksheets, that a regular car, for example, a basic car like Toyota Probox or Fielder, they have a shape, whereas Formula One cars have another shape. Formula cars are actually very low, chapter. The reason is that we expect these cars to have extremely high stability because they move at super high speed. So having them stick to the ground is of paramount importance. So they are designed to be more stable. And this is also true for pretty much all performance car which are also goes into production. They are designed in such a way that at high speed they will be pushed to the ground by the air pressure. They are designed like an inverted wing that works better for them. So
Sir, I had a question.
yes, go ahead.
Sir, where would the center of the mass be if there were people in the bus? Like,
Well,
wouldn't it change?
Well, it depends upon how many people in which deck. If you think that we're going to add equal number of people on both decks, well, C would still be the center of your mass. If you have, but if you have, there's the top deck filled up with people, bottom deck is empty, it will definitely go up a significant amount, which is not recommended. If you are ever running a double decker bus, if the lower side is empty, don't preferably fill up the top end. Don't preferably do that. But then again, if the top end is absolutely keep vacant and people fill up the lower side of the bus, then the COG is gonna even go further down. So it's about the distribution. It's pretty much like the books of the shelf, like people in the bus, books in the shelf, very much like that. Where you place the people, I mean, the more people there is on one side, the more the COG is gonna move towards that side. বুঝা গেছে?
Yes, sir.
এর পরেরগুলো মোটামুটি simple. I don't find any difficult questions over here. So let's go for the one that I was trying to solve for this figure. I did draw the figure for this one, right? Yes. I don't want
জি
to redraw
স্যার,
the figure. এটা লেকচার কি আপ করা হয়েছিল?
আপনি জানেন।
Resume the recording. So currently we are trying to find out how far this person can move. Although it was not more asking my question, but in this case we're going to move this person to the right, so that how far the person can move before the plank topples over, or in other words, that what is the maximum distance the person can move to the right from his original position when this plank is going to topple over. Now the question is why the plank is going to topple over. Why the plank is going to topple over? I want all of you guys to understand this part very clearly. If the person walks slowly to the right, he is gonna increase the RB value and RA is gonna go down, because as he's gonna get closer to the RB, he's gonna applying less force on this support and he's gonna apply more force on the support. When he is gonna cross over to the RB point, let's say when this person has moved over to the RB point on the right side, then one interesting thing is gonna happen. So let me keep the original figure because I might need that. So now if I try to move this person on the right side, where is the eraser? Yeah. So let's get rid of these moments and everything, and the person as well. 520 Newton gone. Let's say this person is going to move to a certain distance on the right side. So we are going to find out that distance. So let's say now the person is located here. And let's assume this is the distance the person can move maximum to the right. So let's say this distance, which I'm labeling as X, is a distance the person can move to a highest, that if he moves a little bit to the right side, this entire plank is going to topple over. Topple over means that he's going to produce so much strong clockwise movement. For example, this value was 520 Newton. So try to understand. Let me draw with purple. Maybe we don't have purple letters over here. In this case, this person is actually producing a very strong clockwise moment about this point. So we are having a very strong clockwise moment like this, whereas this one is about to also producing anti-clockwise moment about this one. Now the point that I want you all kids to understand, whenever the person is going to start walking away from the B support point slowly to the right, he is gonna try to produce the moment about this point. Up to a certain point, both of these support points would have forces, but if this plank is about to roll over, this entire plank is about to have a clockwise motion, the instance when this will happen, try to visualize that. Let's say the person is slowly moving to the right, and at one point this entire plank is actually starting to roll. So this part is slowly starting to go down, this part starting to go up. Obviously this contact point would be lost. Do you agree? The plank is going to lift itself up from this A support point. ঠিক না? বললাম বুঝো? If this plank is starting to roll using B support point as its center, then should it not get off from the support point A? Can you agree on this one?
Yes, sir.
It's going to lift up from that point, and that's going to happen. So if that is the case, in that case, so you can say that very easily that in that scenario of rolling over, RA should be 0 Newton. The reason I am stating this, because for our further calculation, we cannot place the value of RA anymore, because these two values of RA and RB was applicable for the scenario when the person was located over here. And so these values are gone for us. Now the person is starting to move, and the moment the person starts to move, these values would not be this much anymore. They will change. And when the plank is about to roll over, then the reaction force of the A support point, RA, will essentially become 0, which means there will exist only two moments. The person will be producing a clockwise moment about this point using the distance x, which I have labeled, and this weight of 20 Newton will also produce a moment. Should I use a bit thicker line? Maybe should this help? And this plank x would also produce a moment using this much distance. Sorry, not that big. Acha, I might as well, I'll erase it. So this will be the distance applicable for our object x, this rectangular block, that this will use this much distance to produce an anti-clockwise moment, which is going to be pretty big as well. For example, this is going to be the anti-clockwise moment. So because B is going to work as our effective pivot point right now, A is no longer in action, because when the plank is going to go topple over, this plank is going to lift up from A, so A is out of the question. So we now have to calculate that how big is the value of x for this moment to be equal to this moment. So let's go ahead and try this. If we do a bit of calculation over here, we do see that the total distance from this block to the B support point, I mean from here through here, this is 2.5 meter, and the person has moved on the right side by x. So the furthest the person can move, this thing is going to be 20 Newton multiplied by 2.5 meter should be equal to 520 Newton multiplied by x meter. You could give you could also choose not to write the units in the question. Typically we do not write the units in the question, but I'm just writing those units to make sense with you. So this is the equation. এখান থেকে আমরা যদি x কে সলভ করি, x এর ভ্যালু কত আসবে দেখো তো। 20 into 2.5 divided by 520 কত আসে? ক্যালকুলেটর পাইছি, এটা কত আসে ক্যালকুলেট করে দেখো।
0.0962.
0.0962, yes, beautiful. 0.0962. We wrote this is the 3SF value at a meter. So which means if the person is walking to the right of the plank, at most he can move up to 0.0962 meters. whenever he is at this point, we can declare that this plank is currently at critical equilibrium or marginal equilibrium, or it can say it is about to topple over, about to roll over. If the person moves a bit more than this one, this whole structure is going to fall over. This is going to shoot itself in the space, and this person is going to fall down on the right, and this whole thing is going to just not be in equilibrium anymore. So এই ক্যালকুলেশনটা কি বুঝে গেছে কিনা সবার, যেটা কিভাবে করলাম? এখানে দেখো আমাদের পিডিএফটাতেও এই সলিউশনটা করে দেওয়া আছে। এই যে এখানে আমরা পিডিএফ এর সলিউশনটা একটু দেখি। What this solution tells us that when tilt is about to happen, RA equals to 0. This is the first logic that we have to appreciate. That because when the tilt is about to happen, this plank is going to lose contact. This plank is going to lose contact from the RA support point. So taking moment about B point. So we are now taking moment about B point. Now in this case, because I wrote the moment over here, and I still wrote equals to 0 because this was still a case of equilibrium. So I used one moment in one side and the other moment in the opposite as negative moment. And for my calculation, I actually wrote it as same. ওহো, আমি তো দরকারি একটা জিনিস লিখি নাই, আমার ক্যালকুলেশন একটু ভুল হয়েছে। বললাম বলতো কি কি লিখি নাই?
Weight
Of
of the plank.
weight of the plank, exactly. হ্যাঁ, weight of the plank calculate করতে ভুলে গেছে। So I forgot to take this one. I'll have two moments actually. I'll have these two moments counterbalancing this moment. So এখানে actually আর to add হবে। আচ্ছা, forget this. Let me fast write this one. 20 into 2.5 plus 120 into 1 equals to 520 into x. আচ্ছা, এটা আমি করতেছি। এটা হচ্ছে 20 into 2.5 হচ্ছে 50 plus 120 divided by 520.
170.
হ্যাঁ, so we get 0.327. এখন ঠিক আছে। Sorry, I did not read the 120 return first. I forgot the continuation of the math was not in my brain. My bad. So this is the 0.327. So which is actually even smaller than what we have calculated earlier, which was wrong. So this is about this calculation over here, and then we have a little bit of calculation over here. And এই ম্যাথটা কি তোমাদেরকে আগে দেখাইছি কখনো? দেখাই নাই।
না স্যার, দেখান নাই।
আচ্ছা, আমি নেক্সট ক্লাসে আমি এই ম্যাথটা নিয়ে আলাপ করব। A is actually pretty simple to do. B is actually what is interesting. So I'll explain B in detail inshallah next class. আর হচ্ছে এরপর আমাদের চ্যাপ্টার আসবে ওয়ার্কিং algebra. So I'll discuss this problem next class, and then I'll go for the paper 2 discussion for the moment chapter. So we'll do that, and then we'll do the after the moment chapter. We're gonna pick up the next chapter, which is gonna be work energy power. So we have the work energy power over here. Oritri, you asked me another question that when can we have the next booklet? The current booklet is spanned up to work density pressure. So it is a bit unlikely that I'll give you another booklet before I finish up to density pressure. We can choose the next booklet. What the next booklet is going to be? Sorry?
নেক্সট বুকলেট কবে দিবেন?
সেই জিনিসে আলাপ করতেছি। So it's unlikely that you're going to have a next booklet before I finish discussing up to my current booklet, which is up to density pressure. Might take quite some time because we still have 2 chapters to go for. We have work energy power and then density pressure. And after you finish that, I'm going to give you the next booklet. Now, what would be a convenient choice for your next booklet? We can discuss about that depending upon your school. For example, are we going to go in the regular sequence? For example, in the regular sequence for our syllabus, we have kinematics, nuclear mechanics, then we have heat, then we have waves, then electricity, then magnetism, and then the nuclear physics. These are the 6 segments of the syllabus. Now, but for some of you in the schools, they have started electricity as a starting chapter. For some of your school, they have started waves as a starting chapter. So we can have a discussion among ourselves that what can be a preferable choice for the second booklet to be about, depending upon what your schools are doing. It doesn't have to be in the exact sequence of thermal and waves and like that. We can discuss about that, but we're going to have that after some time, after we are done with this worksheet pretty much. I cannot give you a specific date, but it's going to be a while.
Sir,
Yes.
will you publish any workbook for the practical physics?
Currently at this year we have I mean, for the people who are going to appear the O levels exam is the next May June, I'm practicing them the paper 4, which is the alternative to practical. Paper 4 is a good syllabus to go for without the help of equipments, to give the kids a good idea for what to do in the exam hall, what to not to do in the exam hall. I mean, this is a theoretical knowledge base that is very helpful to be used in the lab. If I am still doing online classes and if you're not having actual laboratory classes, then I would introduce you with the paper 4, which is very much possible, and that is a more logical option. Eventually, when COVID things get acceptable and we are actually out of our houses and moving in groups and doing classes and lab classes in groups, when it comes to that level, we can actually start the actual lab classes. But before we go for the practical lab classes, I can help you with the paper 4 classes. Yes, the answer is yes, we can go for the paper 4. তোমাদের স্কুলে কি অলরেডি পেপার 4 করানো শুরু করে দিছে?
আমাদের কিছু ল্যাব করা শুরু করেছে যে ক্যালিপার্স এলিমেন্টস।
স্যার আমাদের স্কুলে পেপার 4 করাচ্ছে।
Acha. So I can actually start with the paper 4. That might happen in the next week. So we can actually define one of the weekdays as a paper 4 class, and other 2 weekdays we can keep for paper 1 and paper 2. That can also work for me, because if it is done, I mean, paper 4 is a pretty simple paper. Once I get you started on the paper 4, you can pretty much do it on your own. And then when you get stumbled onto something, you need help, then I can come back and help on. The actual theoretical discussion to start paper 4 is actually quite small. That's the point that I'm trying to make. And everything, and once I finish up to that point, then it's all about your practice value. So the more you're going to practice, the more you're going to pose me problems with, and the more discussions we're going to have, the better you're going to get at. So I can start that from next week as well. I'll think about it, and then I'll let you know in the next class. এখন 7:35 বাজে, I have to catch another class. So thank you very
স্যার
much. Yes.
স্যার আমরা তো নতুন স্টুডেন্ট স্যার, আমাদের অফিসিয়াল অ্যাডমিশনও হয় না, নোটস এন্ড বুকলেটসও পাই না, স্যার আমরা কি করতে পারি এখন?
গোলাম মুস্তাকিম, তোমার রোল নাম্বার আমি তাহলে আজকে ক্লাসের পর দিয়ে দিব, 1 নাম্বার। আর 2 নাম্বার হচ্ছে ইউ সেন্ড সামওয়ান টুমরো। তোমার বাসা কই?
স্যার ধানমন্ডি 4 নম্বর।
Okay, send someone tomorrow to my coaching. I'll have one set of booklets and all the other stuffs that you starting kids are supposed to have as well. And
স্যার আমি অ্যাকচুয়ালি এখন একটু ঢাকার বাইরে স্যার, আমার ফ্রাইডেতে যাব, তো আমি ওই দিন পাঠাবো।
Okay, ঠিক আছে, fine, ঠিক আছে,
স্যার
সমস্যা নাই। You do that. I'll give you the number for my assistants who will be receiving you and dealing with you and providing you with the booklets. Yes.
থ্যাংক ইউ।
আমিও নতুন, আমারও সেম কেস।
ঠিক আছে, সমস্যা নাই। তুমি কি ঢাকায় আছো?
জি স্যার, আমি ঢাকা।
আচ্ছা, তুমি একটা কাজ করো, সেটা হচ্ছে আমাকে পার্সোনাল মেসেঞ্জারে তোমার একটা কন্টাক্ট নাম্বার পাঠাও। I'll have it prepared and I'll tell my assistants to receive one booklet. কালকে 11টার পর যে কোনো সময় কাউকে পাঠালে হবে।
ওকে স্যার, ওকে স্যার।
Thank you kids. Goodbye.
ওয়ালাইকুম স্যার।
ওয়ালাইকুম আসসালাম।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।